Good morning. This is a video lecture leading up to, or talking about some review topics leading up to a discussion of Chapter 7. And so just remember that in earlier chapters, Chapter 1 and on, we were introduced to stress analysis. In particular, we learned about stress distribution in cross-sections of materials. So in Chapter 1, we talked about sigma is equal to P over A. And in Chapter 3, we talked about tau is shear stress is equal to TR over I. Then Chapter 4 we talked about shear and moment diagrams, and that led us up to Chapter 5 where we talked about sigma in bending is equal to MY over I, and shear stress in bending is equal to VQ over IB. In Chapter 2 also we learned that only axial loads when only axial loads are applied, remember, there's a stress distribution on inclined planes. And so even though it's only loaded axially, only pulling in this direction, there are some shear stresses that are developed on an inclined plane. And so we drew a little stress or a little force distribution, and using statics we found out what P theta and V theta are. And then we found out the normal shear and found out that normal stress and shear stress on that angle are directly related to the axial stresses. However, since stresses are not vectors in the same way as forces, we could not use equilibrium equations to find them. So we had to develop a series of stress transformation equations for axial loads, and those were developed in Chapter 2, and they're repeated here. We also found that the maximum shear stress is half of the maximum axial stress, and that occurs at a 45-degree angle, such that you can see that if you're pulling on this thing and the angle is 0, meaning straight up and down, then all we're talking about is straight axial stress, straight sigma. There's no shear stress on that axis. The same way here, if the angle is at 90 degrees, then pretty much you're taking those two pieces and pulling them straight apart too. So we have all sigma if the angles are 0 or 90 degrees, but if the angle is at 45 degrees, we have the maximum. So what we found is that for all angles, sigma theta on this axis is always going to be less than the sigma in the x direction. So it is generally not going to ever fail in sigma theta. However, if tau max is less than sigma max, then we could have a failure on an angle, another angle due to shear stress, and that's what we discovered with glued joints and finger joint lumber, etc. And so here is an example. Say we have a glue joint on a wood beam, and we suggest that by experiment we've discovered that the shear stress is only a quarter of the maximum normal stress, and we're going to glue this thing at 60 degrees, and that on that angle right there is 60. So we're going to try to find out whether it's going to fail or not. Using our stress transformation equations, we plug those things in, and we discover that tau theta, or the shear stress at 60 degrees, is equal to 0.433 of sigma max. So in this case, 0.433 is greater than the 0.25 that we had determined was our maximum value. So in this case, yes, it will fail in shear before it fails in normal stress. But also we can see as theta increases, it is less likely to fail in shear. So in this case, in this particular example where tau max is equal to 0.25 our sigma max, our critical angle is by plugging those things in here, 0.25, and then just solving for the angle of minus 2 theta over 2. And when you solve this thing, you get a minus 15 degrees. Well, minus 15 degrees is the same as positive 75 degrees. So in this case, where shear stress is maximum of 0.25 of normal stress max, then it would fail at anything less than a 75 degree angle, or an angle between 45 and 75. Alright, so that leads us up then to Chapter 3, and in Chapter 3 we found the stress element to look something like this. When you have a rod or some element in pure shear, in pure torsion you get pure shear, and it tends to make the stress element look like this as you're stressing it on those sides. And again, we found that in pure shear, the maximum torsion is going to occur in this direction. However, on some other angle, like say you had some seam or something on your bar or a weak spot on your bar, that we also have normal stress that occurs at some odd angle, at that angle or at any angle. So we led up to stress transformation equations in shear, which are repeated here, equation 329. And here, in general, the shear stress on this angle is always going to be less than the shear due to TR over I, or the twist. So it generally will not ever fail in shear on that angle. However, it could fail on that sigma angle. And if we found that for some, like especially for brittle materials, that the sigma at some angle could be less than tau, then it could also break due to sigma instead of tau. And we did this class demo with the chalk and found that it broke at a 45-degree angle. And that led us up to chapter 6, where we looked at combined loadings of axial loads and bending loads. And for example, here's a beam under an axial load as well as a bending load. And we discovered that we can add them or subtract those two stresses depending on whether they're on the top or the bottom. And then we also said we have even more combinations of bending and axial loads and torsional loads that we can add together to find out where on any point there is a stress element that can be defined. And we did some exercises on that. Anyway, after we sum all these forces up on that stress element, we create the stress element and say at any point on the beam we should be able to define what the stresses are on that point. And if you recall, we did this one in class, and we talked about the 4 kinds of stresses which we just mentioned there, and the stress distributions, and we did these 2 exercises here in class. All right, well, that led us up then to the analysis of looking at maximum stresses and trying to analyze stresses on different axes. So we know that the maximum stresses are often not on the orientation of the given stress element, which we were defining in just those things. So we had to develop a series of stress transformation equations to analyze the stresses at any angle. And we had some sign conventions about shear stress being the same magnitude on all 4 faces. We analyzed the stress element at an angle, and we came up with the stress transformation equations given here. And those are equations 7, 4. Then we talked about some special cases, and such that these are the general stress transformation equations given that the stress element would have shear and stress in the x direction and stress in the y direction. However, the special cases are, if it's only got stress in the x direction, they reduce to equation 231. In other words, if sigma y equals 0 and tau xy equals 0, then we get the same equations that we had in before. Same if we had sigma x is equal to 0 and sigma y is equal to 0, if the only thing we have is shear stresses, they reduce to equation 329, which we had before. And then the last case, special case, would be if there is no shear, but we have both sigma x and sigma y, they reduce to equation 7.9. Now, we hadn't actually used this one before in any previous work, so that's what we're going into now in chapter 7. All right, and then we did a couple problems in class, which I'll copy here and put on Blackboard for you. I'm not going to go through these again. Then we talked about the principal stresses, how the principal stresses are the minimum and maximum stresses that occur on a particular angle, and we also found some maximum shear stresses. Again, those can occur at some angle from our given angle or a main face, whatever you want to call the given stress element. So we've defined that sigma 1, actually that should be sigma 1, not x1, but sigma 1 and sigma 2. Those should be sigma 1 and sigma 2. So I'll change those on the notes before I copy those. Those are the maximum stress and the minimum stress, and they occur those are the principal angles. The equations for the principal angles and the equations for the maximum and minimum stresses are given here in 711 and 717. There's also a shear stress that is 0. So on the principal angle, as the principal angle is defined, there is no shear stress on that angle. And so if we find the principal angle, then we'll get a sigma. Again, this would be a sigma 1 and a sigma 2, not sigma x1 and sigma y1, but sigma 1 and sigma 2. Those are the principal stresses, and there's no shear on those. All right, then, but we did discuss that there is an angle where maximum shear does occur, and that is defined by that formula there, and that the maximum shear angle, the angle where maximum shear stress occurs is going to be the principal angle plus or minus 45 degrees, and we found out the maximum shear is given by that formula. All right, and then again we did a couple of examples of that. Here's one that has both sigma x and sigma y and some shear, and we did that problem in class. That led us up to Mohr circle, which we did some exercises on that, and that leads us up to a summary then of all the equations that we've been using. So here's a summary of the equations for Chapter 2 and Chapter 3 for stresses on inclined sections. Here are the stresses so far in Chapter 7. So these are the stresses at any angle, sigma x1, sigma y1, and tau on that angle, and then the principal stresses and that we just talked about. And then Mohr circle, those are the equations to begin Mohr circle, and I'm not going to talk about Mohr circle construction in this video. But that leads us then up to where we are right now, and we're going to look at now the stress-strain relationships. We've talked about stresses only, but now we're going to talk about strain, and that's obviously the deformation. And we're going to look at Hooke's law and the strain relationship equations using the strain transformation equations.